In this section, we are going to look at graphing functions. More importantly, we're going to analyze the functions. So not just get the picture, but we're going to use the original function and both derivatives to find out more information about the graph and get a more accurate sketch. In the last section, we talked about looking at asymptotes of functions, and we're going to use that in the analyzing of graphs. Okay, so let's look at how to graph a function. Okay, so given a function f of x, the first thing we're going to do is dissect that information. So we're going to find the domain, find the intercepts, and find the asymptotes. The intercepts and asymptotes are useful because then we get an idea of what's happening in different intervals of the graph. But the domain is important because it gives us the intervals that the function is defined on. Okay? Once we have that information, then we're going to look at the derivative. So I'm going to take f prime and I want to find the critical points. Once we have the critical points, then we want to find the intervals where it's increasing and decreasing, and lastly find the extrema. For the extrema, in this case, we do want to find the ordered pairs. So we're not just looking at the x values, we actually want the points, so we get a little bit more information about the graph. Once we have that information, then we're going to go on to the second derivative. And we're basically going to do the same thing. I want to find the critical points so I can determine what the intervals of concavity are, and then use that to determine whether or not there are inflection points. Okay. Once I have all of this information, I can sketch the graph. So I'm basically going to plot this on a coordinate system, and usually this is going to be enough information to tell you what the graph looks like. In some cases, you may need to plot some additional points just because maybe you don't have a lot of intercepts or there's no extrema. But if we follow these steps, we can get a pretty accurate sketch for the graph. Okay. So let's look at an example. Let's say f of x is 4x over x squared plus 1. Okay. So the first thing we're going to do is we're going to look at f of x. Okay. So I want to start by finding the domain. Okay. And in this case, this function is nice because if I look at the denominator, x squared plus 1, that is always positive. There are no places that is going to be 0. So for this one, our domain is going to be all real numbers. Okay. For the intercepts, remember we set x equal to 0 and solve for the y-intercept, and we'll set y equal to 0 and solve for the x-intercept. In this case, when x is 0, y is 0, so that is both the x and the y-intercept. If I try to set f of x equal to 0, we can see the numerator being 0 says I get this point as well. Okay, let's look at the asymptotes for this graph. So first thing to notice again, like we mentioned before, x squared plus 1 is always positive. So there are no places that's going to go to 0. More importantly, that means the limit as x goes to any value for a is never going to go to infinity because it's always going to be defined. So here we have no vertical asymptotes. If we consider the limit as x goes to infinity of f of x, because it's a rational function, we can pull off the highest powered terms. So we're looking at the 4x over the x squared. And we can simplify. Here we see that when we do that, we get the limit as x goes to infinity of 4 over x, which as that goes to infinity, basically goes to 0. So y equals 0 is going to be our horizontal asymptote. So remember, because the limit goes to a number, it's a horizontal asymptote instead of an oblique, which means that we also have no oblique asymptotes. Because if we did, this would go to an infinity, either positive or negative, and then we wouldn't have a horizontal. Okay. So this gives us the information for our f. So now let's look at f prime of x. Okay. So before we can get information from f prime, we first need to find the derivative. Okay. So, taking our derivative says this is going to be a quotient rule, so we'll take the derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. Okay. Simplifying here, we see we get a 4x squared minus an 8x squared and 4, so 4 minus 4x squared, all over x squared plus 1 squared. Okay, from there we can see first that the denominator is always positive, so again there's not going to be any places f prime is undefined. So f prime is never undefined. So we just need to check when this is going to be 0. So f prime will be 0 when the numerator is equal to 0. So when 4 equals 4x squared, or x squared equals 1, so x will equal plus or minus 1. Okay. And again, to get the increasing, decreasing, and our extrema, we're going to use the number line with those critical points to determine what's happening. So here, some good test points would be -2, 0, and 2. I'm going to plug these back into my derivative. Again, notice the bottom is always positive, so it doesn't matter what I put in there. All I care about is the top. So if I put in a -2, squaring that's going to give me a 4 minus 16. That's going to be negative. At 0, I'm just going to get 4, so positive. And at +2, when I plug in, I get 4 minus 16 again, which is going to be something negative. Okay. So this tells me that my function is going to be increasing on the interval from -1 to 1, and it's going to be decreasing on the interval from -infinity to -1, union 1 to infinity. Okay. For our extreme values, we can see that there's a relative min, so where it's decreasing and then increasing at x equals -1. Again, here we want our ordered pairs, so I'm going to take -1 and plug it back into the original function, and we can see when we do that we get -2. For relative max, we can see that it's increasing and then decreasing at x equals 1. Again, plugging that back into the original function will give me a value of 2. Okay. So now that we've gotten the information for f prime, we want to look at f double prime. Okay. So for f double prime, or our second derivative, we're going to take the derivative again, which is going to require a quotient rule. So looking here, we can see the derivative of the top is going to be a -8x times the bottom minus the top times the derivative of the bottom, which will bring the 2 down front, leave the inside alone, multiplied by the derivative of the inside. So there's that chain rule again. Oops. And we're going to square the denominator, which was already squared. That makes it a 4th power. Okay. Combining like terms and noticing that there's an x squared plus 1 in every term, we can go ahead and divide that out. So we're going to get an x squared plus 1 cubed on the bottom, which means I'm left with basically one of those, none of those, and 3 of these. So combining terms, we have an 8x cubed, a -8x cubed, plus a 16x cubed, a -8x minus a 16x. So there's our f double prime. And again, just like f prime, we can notice that the denominator here is always positive, so f double prime is never undefined. Okay. So now we're going to find the critical points by letting f double prime equal 0. So again, that just means I'm looking at when the top 8x cubed minus 24x is going to equal 0. Now notice I can factor this, so 8x, I can pull out x squared minus 3. So x will equal 0, or x will equal plus or minus the square root of 3. Okay. So on my number line here, again, I want to test points in each region. So root 3 is about 1.7, so I need something further. So -2, -1, 1, and 2 will work. Again, I'm plugging this into the derivative, the second derivative here. Again, the bottom is always positive, so I only care about what happens on the top. Okay, so if we notice that 2, 8x cubed, that's looking like 64 minus a 48. That's certainly going to be positive. At 1, I get 8 minus 24. That's definitely negative. Negative 1 will give me a negative 8 plus 24. And at -2, I'm looking at a negative 64 plus 48. So that's negative. Okay. So for my concavity, we can say this is concave up on the interval from -√3 to 0, union √3 to infinity. It's going to be concave down from -infinity to -√3, union 0 to √3. Okay. And then inflection points, again, are going to occur where the second derivative is 0 and it changes sign. So we have inflection points at 3 different spots. Notice at 0, get your value there, which we know is 0. That's one of our intercepts. At √3, if I plug that into the function over there, we're going to get 4 square roots of 3 over 4, which is basically just √3. And if we look at the negative √3, we're going to get a negative 4 √3 over 4, which again is just going to be negative √3. Okay. Now that we have all this information, we want to plot this on a number line. Okay. Or sorry, on a coordinate system. Okay, so we're going to start back over here with the information from our function. The domain is all real numbers, so I don't have any vertical asymptotes. I know that there's an intercept here at 0, 0. I'm going to make my intercepts big so that you can see them on there. No oblique asymptotes, but I do have a horizontal asymptote at y equals 0. Okay, and I'm going to put that in red so you can see it runs right along that x-axis, but that's an asymptote. Now remember, for your horizontal and obliques, it doesn't matter that I cross them, it just matters that as x goes to plus and minus infinity, that's where my graph is going. So out here on the ends, I know it's going to be close to that x-axis. Okay? Coming down our information, we see that we've got a relative min at the point -1, -2, and a relative max at the point 1, 2. Okay. Inflection points at 0, 0, at square root of 3, so over in here, square root of 3, so somewhere, sorry, square root of 3 is about in here somewhere, and -√3, which is going to be in here somewhere. Okay. We have that from -infinity to -1, it's decreasing. So coming this way, it's decreasing, and up into negative root 3, it's concave down. So that tells me it's going to do something like this. So again, there's that subtle concave down. It's going to keep decreasing to negative 1, but between negative 3 and 0, or yeah, negative 3, root 3 and 0, it's concave up. So it changes from a subtle concave down to a subtle concave up. At negative 1, I'm going to change to an increasing and concave up. And then at 0, I'm still increasing, but now I'm concave down again. So it's going to change to that direction. Okay. At positive 1, I'm still concave down, but now I'm going to be decreasing till I get to my root 3, where it's going to change back to concave up, but I'm still decreasing. And then I'm going to go off to infinity. Okay. So there's our graph of f of x. So let's look at another function. This one we're going to look at is an exponential, so f of x equals 12e to the negative x. Okay. So again, we're going to start with our f of x. Okay. So for this one, looking at the domain, we can see, well, 12 is a constant or a coefficient in this case, and e to the negative x, we know e to the negative x is defined everywhere. So here again we have domain negative infinity to infinity. For our intercepts, when x is equal to 0, we can plug in and see that we're going to get 12. And if we try setting it equal to 0, well, we see 12e to the negative x equals 0, never, right? If you remember your exponentials, it's defined so that the range is always 0 or above, above 0. So there's our only intercept. Okay, let's look at asymptotes. Again, it's defined everywhere, so this tells me there are no vertical asymptotes. If we look at the limit as x goes to infinity, we can see this is going to be basically the limit of e to the negative x as x goes to infinity. Well, thinking about this logically, as x gets big, negative x becomes really negative, and e to that goes to 0. So this is going to go to 0, which tells me that's my horizontal asymptote, and there are no oblique asymptotes. Okay. Now that I have the information from f, we want to look at f prime. Okay. So again, we're going to start with the derivative. So f prime of x looks like, well, 12e to the negative x is a chain rule, so it's itself times the derivative of the exponent, which is just negative 1. So here, this is going to be negative 12e to the negative x. There's our f prime. Again, notice this is just an exponential, so f prime is never undefined. Okay. So here we just need to determine when f prime is going to equal 0. So looking at negative 12e to the negative x, we want to know when this equals 0. Well, again, in this case, this is just an exponential. Exponentials ranges above 0, so it's never going to equal 0. So this tells us there are no critical points. So to determine increasing and decreasing, I basically just need to pick any value on the number line. So if I look at my number line, again, domain is all real numbers, I pick any value. Let's try 1. Okay. If I plug in to my derivative, so plugging in here, I'm going to get negative 12e to the negative 1. Well, e to the negative 1 is still positive, but that negative 12 out there means that's negative. So this is decreasing from negative infinity to infinity, which means there are no intervals where it's increasing and no extrema. Okay. Alright, so now let's look at f double prime. Okay. So f double prime, we're going to take the derivative of negative 12e to the negative x. Again, it's itself, so negative 12e to the negative x times the derivative of that exponent. So we're going to get a negative 1 when we multiply that out, which will give us 12e to the negative x, which is basically the function we started with. Okay. Here again, e to the negative x is never undefined, so f double prime is never undefined. And if we try setting this equal to 0, again it's an exponential, so f double prime is also never 0. Okay. So again, what this means is when I go to look at concavity and inflection points, I just need to pick any value in the domain to see what the concavity is doing. So here again, let's try 1. If I put in 1, I'm going to get 12e to the negative 1, which again is just a positive value. So it's concave up on the interval from negative infinity to infinity, never concave down, and there are no inflection points. Okay. So let's look at the graph here. Okay. So with the information that we found, let's go back to the beginning. We're going to change our scale a little bit. So let's make this by 2's. Domain's all real numbers. Intercept, we have one up here at 12. So we'll make that kind of big. Let's see that. No vertical, no oblique asymptotes, but there is an asymptote here at y equals 0. So again, our y-axis, or sorry, x-axis. Okay. No critical points, meaning there's no extrema. It's decreasing everywhere. There's no inflection points or concavity, and it's concave up everywhere. Okay? So just because I know it's concave up and decreasing, it tells me that my graph should be doing something like this. And we can check that by picking any point. We can pick a point over here, say negative 1, and we'll see that f of negative 1 is going to be 12e. And if we pick something on the other side, say positive 1, we can see that f of 1 is 12e to the negative 1. Okay, so the value here is bigger than the value here. We can see that this does in fact work for our graph. Alright, let's look at one last example, and that is f of x equaling 3x to the 4th plus 1 over x squared. Okay, we want to sketch the graph of this function. Okay, so again we're going to start by taking a look at f of x. So here, if we look at our domain, we notice that x squared in the bottom means that x cannot equal 0. Okay? That seems to be the only problem spot. So negative infinity to 0, union 0 to infinity is going to be our domain. Okay? For the intercepts, well, plugging in x equals 0 is problematic because we just said x equals 0 is not in our domain. And if we look at trying to set this equal to 0, we get 3x to the 4th plus 1 equaling 0. That's going to give me a negative inside of a root. So here, there are no intercepts. Okay. For the asymptotes, if we look, here, because 0 was problematic, the first thing we should note is the limit as x goes to 0 from the right or from the left. These values, as x goes to 0, the top doesn't, but the bottom does. So these are going to go to some infinite value. Okay, this tells me that there's a vertical asymptote at x equals 0. If we look at the limit as x goes to infinity of our function, we can see, again, looking at highest power terms, 3x to the 4th over x squared. That'll simplify down to a 3x squared, which goes off to infinity. This tells me there is no horizontal asymptote, but there is an oblique. To find the oblique asymptote, we are going to need to do division. So if we look at how many times x squared will go into 3x to the 4th plus 1, notice I didn't write the plus 1 yet, and that's because if I look at this, I know this is going to go in here 3x squared terms, so I'm going to need an x squared placeholder. Okay, and when I divide out, I can see that I'm just going to get a remainder of 1. Basically, this will be 0, this will be 0. Okay, so I just get a remainder of 1, which means this is my g of x. Okay, so our oblique asymptote is y equal 3x squared. Okay. Now that we have the intercepts and the asymptotes, let's look at f prime. Okay. For f prime, we need our derivative, so we're going to have to use a quotient rule here. So the derivative of the top is going to be a 12x cubed times the bottom minus the top times the derivative of the bottom, all over the bottom squared. Okay. Notice some of the x's will cancel out. 1x will cancel out of everything here. So we're left with 12x to the 4th minus a 6x to the 4th plus, or sorry, minus 2 over an x cubed. Okay. Using that as our derivative, we can see that f prime is undefined at x equals 0. And for this one, because of that minus in the top, I can see that f prime will equal 0 when 6x to the 4th is equal to 2. So we can solve by dividing out by 6. So x will equal the 4th root of a third. Okay. Because it's an even root, remember your even roots, we're actually going to get a plus or minus one there. Okay. So looking at our number line, We're going to plug these values in there. So there's the negative root, fourth root of a third, positive fourth root of a third, and 0. And we're going to test something in each region. So 1 and negative 1 are definitely going to be in there. And then we need some small numbers in here. Okay. So I'd say, so in here we can use something like 0.1 and negative 0.1. Okay. You can actually plug in and get a value for these, and it comes out to about 0.79. So you can use other values, but those are nice ones to try out. Okay. Again, these we're testing into the derivative. So if I put in 1, I can see I get 6 minus 2 on the top over 1. That's certainly positive. At the negative 1, I'm still getting a 6 minus 2 on the top, but on the bottom I'm getting a negative value. At 0.1, this becomes very tiny, so that's going to be a negative number, and then it's positive on the bottom. And here, again, this will be a really tiny value, minus 2, so something negative, but the bottom is also negative. Okay. From there, we can see that we're going to be increasing from the negative fourth root of a third up to 0, union the fourth root of a third to infinity, and decreasing from negative infinity to a negative fourth root of a third, union 0 to the positive fourth root of a third. Okay. For the extrema, we have a relative min, where it's decreasing and then increasing. So here at the negative fourth root of a third, again, we want to plug that in and find the y value. So notice here, if I take the fourth root of that, I'm going to get a negative 1 plus 1. I take that back. We'll get 1 plus 1, which is 2, over the square root of 1/3, which is basically 2 root 3 over 3. You can check that. For the other side, I've got it decreasing and then increasing. So again, I've got the positive fourth root of a third. And when I plug in, notice it's all squared, so I'm going to get the same value for that one. Notice here for relative max, it's increasing and then decreasing, but at x equals 0, my function was undefined. So for relative max, there actually is none. So now with that information, we're going to look at f double prime. Okay. So f double prime, we're again going to take our quotient rule to find our derivative. So here, derivative of the top is going to be 24x cubed times the bottom minus the top times the derivative of the bottom all over the bottom squared. For this one, we can take an x squared out of everything. So we're looking at 24x to the 5th minus 18x to the 4th minus the 3 will stay there, so plus 6. And I apologize, that's a 4th. So we're pulling out 2 of those. And on the bottom, an x to the 4th. Combining those like terms, we get f double prime is going to be 6x to the 4th plus 6 all over x to the 4th. Again, notice the x fourth in the denominator says that f double prime is undefined at x equals 0. Notice in the top I have only positive values, so 6x to the 4th is positive and 6 is positive, so f double prime is never 0. So on our number line, we just have the 0 that we're looking at. We need something on either side. So negative 1 and 1 will work. At 1, plugging in, the top is positive, the bottom is positive. At negative 1, the top is positive, the bottom is still positive. So here this tells us that our function is going to be concave up from negative infinity to 0 and 0 to infinity. It is concave down, never, and there are no inflection points. Okay. Again, 2 reasons. 1, there's no sign change, and 2, because the 0 comes from where it's undefined. Okay. So, for our graph, so we'll start back over here with the information that we have. So there are no intercepts, but we do have a vertical and an oblique asymptote. Okay. So here our vertical asymptote is at x equals 0. Okay. And our oblique asymptote is 3x squared. Okay. So 3x squared is basically a parabola that looks like that. Okay. So again, can't cross the vertical asymptote. Horizontal I can cross, but as I get further out, the end should look like that red dotted line. Okay. From here, we have 2 relative mins at positive and negative 4th root of a third. Again, if you plug that in, you'll see it's about 0.79, and 2 root 3 over 3, that means we're looking at something up in here and up in here. Okay. No inflection points, always concave up. Okay. So from negative infinity to our min, we are decreasing and concave up. From there, we are concave up and increasing. Same thing over here. On this side, from 0 to infinity, we're concave up. We start out increasing and then, start out decreasing and then change to increasing. So concave up, decreasing, and then concave up, increasing. Okay. So there is the graph of f.